So this is number 19. It asks, what is the frequency of radiation that has a wavelength of 10 micrometers, about the size of a bacterium? So it wants to find frequency, so we're looking for nu. Nu is equal to c divided by lambda. So c, of course, is the speed of light, 3 times 10 to the 8th, and that would be meters per second. And then we need to put the wavelength down here and make sure that it matches the units up here. So make sure that it's in meters. So it says it's 10 micrometers, and a micrometer, remember, is 10 to the negative 6th of a meter. So we'll write it as 10 times 10 to the negative 6th meters. And then we can take those two numbers and divide them, and we end up with 3 times 10 to the 13th per second, or seconds to the negative 1, because notice how meters will cancel with meters, because when you have units over the top of one another like this, remember this would be like meters over 1 like this, multiply by the inverse, so it becomes 1 over seconds as our units. And if you don't like to write 1 over seconds, you can write seconds to the negative 1 and you'll be absolutely fine. Letter B, what is the wavelength of radiation that has a frequency of, so now we're given the frequency and it wants us to find wavelength, so wavelength is equal to c divided by nu. C, once again, is 3 times 10 to the 8th meters per second, and then nu is 5.5 times 10 to the 14th per second, so 1 over seconds. You can see how the units work again right here. You're going to multiply by the inverse, so you have meters per second times seconds over 1, so the seconds cancel, so your answer should be in meters. So when you divide those two, you end up with 5.45 times 10 to the negative 7th meters. Letter C, would the radiation in part A or part B be visible to the human eye? So now if we're looking at both of these, we'd have to put those onto a spectrum chart. So your spectrum chart right here can be really helpful either way. And we want to know if it's in this visible region right here. And the visible region for wavelength is between, probably easier to see on this side, right in this area right here. So the wavelength would be in meters, between 10 to the negative 6th and 10 to the negative 7th. So that puts us really close right here. And if you look at it in, I believe it gives it to us in nanometers, it's between 700 and 380 nanometers, and this would be 545 nanometers, so we're right in between those two. So yes, this would be in the visible spectrum right here, letter B. The letter A right here, this is a frequency, and so we need to look for something times 10 to the 13th. 10 to the 13th, this is 10 to the 12th, this is 10 to the 14th, 10 to the 13th would be right here, which would put us in the infrared region or IR region for letter C. So B would be in the visible spectrum. And then lastly, letter D, what distance does electromagnetic radiation travel in 5 microseconds? So in this case, we want to find out how far it goes. We know that the speed of all electromagnetic radiation is 3 times 10 to the 8th meters per second. If we multiply it by the number of seconds that it would be going, we'd know the number of meters. And this says microseconds, so 50 times 10 to the negative 6th seconds, because micro means negative 6th. The seconds cancel with the seconds, and then you can add the exponents there. That would give you positive 2 for exponent to the 2. 3 times 50 is 150, so 150 times 10 to the second, or if we move the decimal point 2 places over, 1.5 times 10 to the 4th meters is the distance that it would travel.